So I want to talk to you in the next minutes about finding longitude and all sorts of other nonsense, but that title would have been too long. Let's face it, the sea is not your friend. More often than not, in particular, if you sail the seas in the 18th century, you might start off and never arrive. And as an example, in 1707, some ships of a British fleet in the middle of a war going home missed their way and actually hit the Skinny Islands. 4 ships sink, more than 1,000 souls lost, there are 13 survivors. One of them, so the story goes, is basically the boss. So Chauvel, the commander of the British fleets, he barely makes it to the beach and there can contemplate one of his big errors in life. Just the morning before, he had someone executed for daring to tell him that his navigation was off. Well, maybe he should have listened, because then maybe he would still be on the ship. Now, surviving is a good idea. Surviving with a beach robber nearby is not. The beach robber fell in love with a ring. And rather than just kindly asking, can I have a ring? Well, she decided to better just kill him. And she would only confess to that deed years later on her deathbed to a priest. Now, that's the kind of story we like to hear. Of course, half of it is not true. The truth is, of course, that the ships did sink. More than 1,000 souls did get lost. Well, there was no beach robber robbing any ring of that captain, and he probably did not execute anyone beforehand either. But what this story tells us, indeed, navigation on sea is important, because if you don't know where you are, you may find out too late. So, given this catastrophe, the British public, of course, was forced again to rethink these troubles with navigation. And how do you solve a problem if you don't know the solution? Right, you form a commission. And I did not say commission of inquiry. What the British Parliament did is they passed the so-called Longitude Act. And they set forth a considerable prize money for whoever solves the problem of navigating, and in particular of navigating east-west. And if you look at the amounts, 42 million rand for just being able to tell someone whether he's off by 100 kilometers, that's not too bad, right? It shows you how big the problem was. I mean, navigating was guesswork. Let me come to that. How they guessed in a short while. And going up to something like 20,000 pounds, which 84 million rand in today's terms, that's really a lot of money. It should come as no surprise that all sorts of people came up with proposals how to solve the problem. But we will see later how it eventually was solved. But you might ask, and rightly so, why is navigation so difficult? I mean, today we would just put out our phone, right, and ask Google, and problem solved. The problem is, of course, that in the 18th century, there was no Google. So what can we do? Now, obviously, the problem of navigating can be divided into 2 parts, navigating north-south and navigating east-west. Let's take the easy one first, navigating north-south. How can I find out how far north or south I am? There is a simple solution to that. You go, find someone with a protractor for measuring angles and grab that protractor. Then you go to your neighbor and you hope that your neighbor has a sundial. And then you just measure the angle of the stick or gnomon, as it's called, of the sundial, and that angle will tell you how far north or south you are, because that angle actually is your latitude. Now, easy enough, right? The only problem is that there are so few sundials at sea. So we have to come up with a better plan. Well, luckily there is one. We basically just have to wait until it's nighttime. And then we just have to look at how the stars are moving. And if you follow a star throughout the night, you will actually see that it seems to move in a circle. That should come as no surprise because our Earth is rotating after all. And so from our point of view, the whole sky is rotating around some axis. And the axis is, of course, on our hemisphere due south. And basically, if you measure the angle of that point, which is fixed, of the axis to the ground, you've got the latitude. Hooray, that's reasonably easy, right? Now, of course, you have to do these things precisely. So you need some proper instruments for that. The sextant is a good choice for navigation on sea because the sextant is basically measuring angles. But the cool thing about the sextant is it basically measures angle differences. And so it doesn't really matter whether your ship goes up and down, your reading will stay the same. That is really helpful, and I can show you how that works. So basically, if you navigate with the sun, you would basically find the sun, make sure that by turning the sextant, it aligns with the horizon. You would make sure that it really does, that the limb touches the horizon, and then you could read off the angle. Nothing in life is easy, right? Contrary to the stars, you can't just do that with the sun the same way every day because, as we of course all know, how high up the sun is in the sky depends on the season, which of course is directly related to the fact that our Earth axis is tilted. But that is really a story for another day. The bottom line is navigating north-south, at least conceptually, is really, really easy. Tick. Navigating east-west. So the problem becomes apparent if you look at maps. This is an example of a map, and it happily shows you what we might call zero longitude. Well, it's obviously not going through Greenwich, right? Well, we would expect it. The prime meridian is completely off. And we can find all sorts of maps which put the zero longitude as prime meridian anywhere. What does it tell us? It seems that there is nothing special about the prime meridian. Anyway, that makes sense, right? The Earth is rotating around its axis, and it doesn't matter how far east or west you are, as the Earth is rotating, you will be in the same spot sooner or later. What that means, of course, is you can't just use the stars or the sun or whatever for finding out how far east or west you are. That was a real showstopper. Navigating east-west was basically guesswork. So how do you guess where you are? Well, one way is what you call dead reckoning. And dead reckoning basically means that at some point in time, you know where you are, and then basically you measure your speed in the direction, and then you calculate where you should be from the speed in the direction. Now, the word dead reckoning comes from deduced reckoning, because it deduced where you are from observations. However, in some respects, the word dead is much more appropriate, because if you use dead reckoning, chances are that you are dead soon. But how is dead reckoning actually done? Let me ask a question first. I don't know how many of you are using computers. If you do, you may have seen a log, right? Or you may have a log in your car for SARS or whatever, right? Have you ever wondered why a log or a logbook is actually called logbook? I mean, what does it have to do with a log? you would think nothing, right? It actually has something to do. Because how would you actually do data reckoning on a ship? Well, you start from some known position, and then you somehow have to figure out how fast you are. Well, what do? Essentially, you throw a piece of wood, a log, into the water, and then it floats away because the ship is moving, and then you have, oh, sorry, I should not move away for the night. And then you have a rope, which is, of course, then winding down, and you let that slip through your hand, and this rope has knots. And so basically, you have a set clock measuring something like 28 or 30 seconds, and you just measure the number of knots passing through your hand at that time. And that, of course, gives you your speed. And surprise, surprise, that is why ships have speeds measured in knots. It comes from that way of actually reckoning your speed. So that is, of course, not perfectly accurate because there might be all sorts of problems with that, but it was what they had. Well, maybe it should come as no surprise that they had shipwrecks every once in a while. So there must be better ways of doing that. And tell you what, in principle, solutions were found, I think, in the 1st century BC already. Actually, the Greek astronomer Hipparchus already pointed out a solution. You can use a lunar eclipse. And this is actually a picture taken recently when there was a lunar eclipse here in Cape Town. The cool thing about the lunar eclipse is you can basically see it from everywhere as long as the moon is above the horizon. And the other cool thing is you can predict when it happens. And that goes to the core of the problem of navigating east-west. The problem of navigating east-west is that I don't really know what the time is. Because if I knew what the time is, what I basically could do is I could check when does the sun rise. I know at what time it is supposed to rise. I know what the time really is compared to, say, Greenwich. And then I can figure out how far east or west I must be from Greenwich. So if I have a clock which is accurate, I'm sorted. Because I can tell local time. And that is a clock. And it is available. The problem is, of course, it is not easily available because lunar eclipses are not that often after all. We have to wait for our next one 3.5 years. So that's a good way for basically estimating, say, longitudes on land, where you have plenty of time available. You miss a lunar eclipse, no problem, you wait for the next one. No big deal. If you're on a ship, waiting for the next one is simply not an option. That does not mean that lunar eclipses have not been used. I know of at least one case, and that has a connection to Cape Town. Now, I don't know, does anyone know that gentleman on the right-hand side? Yeah. Pardon? I would be surprised if you had asked me 20 years ago before I came here, I wouldn't have known him either. It is actually a French astronomer called Nicolas Louis de la Caille. And you probably look at me and say, who? Fair question. La Caille is pretty unknown today. However, he did something pretty cool. Because he not only measured about 10,000 star positions when he was in Cape Town, he not only tried to measure the shape of the Earth and figured out incorrectly that it was pear-shaped. No, he also named 14 of the southern sky constellations. Rule of thumb, to find them, look for 18th century high tech. If you find constellations like the pendulum clock, the telescope, the chemical furnace, you know whom to blame. It was that time. If you're not into 18th century high tech, there still is a very cool constellation name he chose. In Latin, Mensa or Mons Mensae. And if you translate that into English, you end up with Table Mountain. That makes our Table Mountain one of the very few real geographical objects in the whole world after which a constellation is named. Okay, I digress. What does Lacaille have to do with lunar eclipses? Now, I told you that he was measuring star positions in Cape Town, which implies that he must have come to Cape Town, obviously by ship. Now, the planned route was basically go from France to Cape Verde Islands, inside that red circle, and then to Cape Town. So they started off. And then after a while, there was a lunar eclipse. And again, that is a good clock. You can use that to figure out how far east or west you are, which Lacaille did, only to figure out that they were further to the west than expected. They had missed the Cape Verde Islands. So instead, they went on to Brazil and then back to Cape Town. That is how bad the situation was in these days. Okay, so in principle, lunar eclipses work. The problem is they are way too rare. Next plan. We move to the year 1609. An Italian physicist called Galileo Galilei, you may have heard of him, well, has the idea that you can use a telescope to look at something up there. And he looks, among others, at Jupiter. And surprisingly, he sees that in addition to Jupiter, you can see some moons around Jupiter. And obviously, what do moons do? They orbit a planet. And they do that fairly regularly. So again, you have a clock. Basically, you only have to figure out with what frequency do these moons appear, and then you can basically figure out from when the moon comes what the time is. Brilliant, right? Problem solved. Well, it works at land, more or less. At sea, making precise observations is a bit difficult if your ship is going up and down and it's cloudy and you have all sorts of other problems. So works in principle, does not work in practice. So, but it has an interesting consequence. Now, people now, of course, try to use that method for measuring longitude, and on land it works. So they do that. But then they figured out that there is a problem, and that is linked to the name of Ole Rømer, a Danish physicist, who, well, or maybe it was not him, but Cassini, an Italian astronomer, but he really propagated the theory then. They spotted the problem. Now, you would assume that the moons of Jupiter move around Jupiter very, very regularly. So basically, you say if they appear every 42 minutes, they really appear every 42 minutes, right? If that was the period, which it isn't. But what they realized is that it depends on the season. Sometimes the period is shorter, sometimes it is longer. And it actually depends, more technically, it depends on whether the Earth is moving towards Jupiter or the Earth is moving away from Jupiter. Why could that be? Well, Römer argued, it probably means that there is something we might call the speed of light. Because if the Earth is moving towards Jupiter, say your first event happens at some time, and then the light from the second event, when the Io is in the same, the moon is in the same position, does not take as long because, well, sorry, I'm on the right side. Basically, as the Earth is moving towards Jupiter, obviously the next time, the path the light has to travel is shorter. So it doesn't take that long. So the period will be shorter. On the way back, now, of course, with the Earth moving away from Jupiter, it takes longer. Now, if you read that in physics textbooks, you would be forgiven to believe that Römer came up with a theory and everybody said, yay, we have found the speed of light. Of course, science usually does not work that way. What happens is someone says, yay, I have found the speed of light, and all the rest says, we're not so sure. So maybe it's another problem. And when it came to other moons of Jupiter, the measurements were not that conclusive. So actually, it's not that everyone all of a sudden believes we have found the speed of light. That question was only settled later when another astronomer found what we call aberration. It depends on the season at which angle to the vertical you can see a star. And it also depends on your latitude. And why is that? I mean, it has to do with the motion of Earth. And it is something you might know from everyday life. Imagine you're in a car and it's raining. And it's raining, you are standing still, and the rain is coming from the top. Right? What happens if you start driving? Well, the rain will now come at an angle, right? Always coming from the front. Why is that? Well, it's simply because you have got basically the velocity, the motion of the rain relative to the ground, but then you also have the ground moving relative to the car. And if you're in the car, that means relative to you. These velocities add up, these motions add up, and so, as seen from the car, the rain now has a different velocity and hence a different direction. Works for rain, works for light as well. So that is why you have this aberration of starlight throughout the seasons. And that seems to have convinced people. And of course, later on, physicists became able to actually measure the speed of light with experiments, and that, of course, settles the question once and for all. So, nice, we have learned that there is a speed of light. We haven't solved the problem yet. We still have to navigate east-west. And now there is one friend in the sky which might help, the moon. Because the moon obviously is orbiting around the Earth. And that means that it will actually change its position relative to the stars all the time. And so in principle, if I knew at what time the moon would be where precisely in the sky, well, I just have to look where is the moon, and I know what the time is. Well, basically, what I have to do is I have to measure the distance between the moon and maybe the sun, maybe a star, and then I have to correct for the fact that light is reflected in the atmosphere and the point of view of the moon changes with the latitude and all that nonsense, but you can correct for that. Also just by measuring angles. So, problem solved, right? Apart from the fact that there is a problem. We've got, in order to describe the motion of the moon, we've got the Earth, the moon, and the sun. It's a three-body problem. And the problem with three bodies is you can't solve the equations of physics for that analytically. There is no nice, easy solution. And actually, the motion of the moon is fiendishly difficult. And that is why it took really, really long before astronomers actually had been able to basically calculate the motion of the moon sufficiently accurately so that they could actually use it. And that, as I said, solves the problem. Now, it still means a lot of calculations at sea. It also means that you basically have a table of moon positions taken with you, and it still doesn't help you if the weather is bad. Is there another solution as well? And yes, there is. And that came as a real surprise. And that solution was found by John Harrison. John Harrison from Scotland was a clockmaker. And we have absolutely no idea where he learned the skills he had, but he was really skilled. And he had the idea that maybe it is possible to build a clock which will work on board of a ship. That sounds easy to us. But what did clocks look like in the 18th century? I mean, pendulum clocks, right? the pendulum swinging. Now imagine the pendulum on a ship going up and down, going sideways, being in storms, moving through different climate zones. Won't work. It is simply not accurate enough. So pendulum clocks work fine on land, they don't work on the ship. So Harrison set out to do something about it. Not least because, remember, there was that longitude act, right? There was real money to be won. So he spent 5 years building his first clock that was actually tested on the ship and actually quite successfully, to the extent that on the return journey, the captain and the clock differed by about 60 miles or kilometers, and the captain was one. The clock was so accurate. But that test on the ship just to Portugal did not satisfy the requirements of the Longitude Act. So he kept going. And he spent another 3 years building his second clock and then tested it for 2 years on land. It was never tested on sea, not least because there was war at the time and the Britons had no interest in, say, the French getting their secret here. And then Harrison discovered that there was a flaw. So he abandoned working on it, and instead he turned to building his H3, 17 years. Now that's dedication, right? Now luckily he did get some funding from the board of Longitude. That was the commission responsible for educating anyone who wanted to get that prize for finding the longitude. Alas, despite working on it for 17 years, it never really worked to his satisfaction. And then he had the idea that maybe you can actually make it very compact. And he spent another 6 years building his fourth clock. And that was actually successfully tested at sea in 1761. And then the board of Longitude basically said that, yeah, it fulfilled all the requirements, but it might have been good luck. Let's try again. So they tried again, and it worked again. And they said, yeah, we give you half of the money, fair, but now you have to produce another clock, and please give us the instruction on how to do that. Someone else must be able to build it as well. Thank you so much. And Harrison and his son William were not particularly happy about that. It ended up eventually going to the king, actually, who then tested a fifth version of the clock and basically then told Parliament, hey, either you give him some money now or I pitch up here. And then Parliament decided, yeah, maybe we should give him some money. That is actually linked to an astronomer. That was the Astronomer Royal, and ex officio was part of the board of Longitude. And there may have been a bit of animosity between Harrison and Mascarene. He was more on that side of using lunar distances, whereas Harrison obviously propagated the idea of using clocks. The truth is that neither of the methods alone really solved the problem. Because even if you have a clock, you must have a way of checking your clock. Even if you have lunar distances, you must be able to find out where you are if the weather is bad. So they really go together. So it's a bit sad that they were sort of enemies. Whole novels have been written about that. Whether the animosity portrayed in certain books is really entirely correct to that extent is another question. But there must have been no friendship lost between the two. And again, but sad because at the end of the day, you need both methods. But once you had both methods, you could all of a sudden actually navigate east-west. And that, of course, was a game changer. To give you an idea of how important that was, not only did it mean that Mascarene, the astronomer on the right side, started in 1867 with an 1767 with an annual publication of these tables of lunar positions year after year until he died in something like 1811. And actually, these tables still are published in a different way. They are called astronomical almanac now, but that still exists. Yeah, so where was I? Anyway, yes. So clearly there was motivation to get these things out. On the left-hand side, the first clocks, Harrison built and others built, and of course, were not cheap. Actually, I read that such a clock initially might cost about 1/3 of the total cost of a ship. That's not cheap, but they were still bought because they were so important. So now, with the problem essentially solved, at some point the board of longitude obviously became more or less obsolescent, but before it was formally dissolved, they still made a very nice proposal, which was to build the Royal Observatory in Cape Town, which is, of course, where we are. Of course, today it's the South African Astronomical Observatory, but that was the forerunner. So I think that's quite nice of them. And what was the job of the astronomer here? Apart from measuring star positions, giving time signals. Because obviously people had to take their time on board. They had to make sure that the chronometer was actually working properly or how far off it was. And I already mentioned the publication of the almanac. Now, the publication of the almanac had a consequence, because that almanac was widely used not only by British seafarers, also by others, and it was based on the Greenwich meridian. So now a wide part of the world having at sea was actually using values based on the Greenwich meridian. And that is at least part of the reasons why I think in 1884 at an international conference, everyone agreed that the meridian through Greenwich should be the prime meridian, 0 longitude, right? So these days you can go to Greenwich, right, in London, go there, and on one side on the east and on the other side of the rest of the earth, right? As shown here, right? True? Not quite. If you do that with your GPS, it will actually tell you that right on that meridian line in Greenwich, you are not at 0 degrees. You are about 100 meters off. Why is that? Well, our modern measurements have become so accurate that we have figured out that basically the meridian through Greenwich does not define the plane which goes to the center of the Earth. It's slightly off. And that is not good for modern navigation, and that is why I think in the 1970s, a new meridian was defined, which happens to be 100 meters off. Well, I don't think the tourists necessarily know that. And of course, these definitions of a new meridian are closely linked to the fact that we nowadays have much more accurate clocks. And of course, the most accurate clocks we have at the moment are atomic clocks. And they basically make use of the fact that you can excite an electron in an atom, and you need a very, very precise frequency of light for that. So what you make sure is that you tune your frequency so that you basically excite more or less all atoms, and then you know that frequency very accurately. And then you basically just have to count waves and you get time. That's basically how we measure time these days. There are plans to move to something else. Now you don't excite an electron, you now excite a nucleus, which is even more accurate. So we might get much more accurate times very soon. That is crucial for everyday life, because how do we navigate today, right? We use GPS. How does GPS actually work? Now, you have this network of satellites, and each of these satellites has such an atomic clock on board. And it is happily sending signals all the time, which your GPS receiver in your car is actually receiving. And basically, these signals have a position of a satellite and the time when the signal is emitted. And if you have one satellite, basically you can figure out from these time signals in your own time, right, where you are on the surface of a sphere, which is not particularly helpful. But if you have two satellites, now you can basically measure the position relative to both of your satellites, and you narrow down your potential position to a circle where these two spheres intersect. Well, if you have three, you narrow down your potential positions to 2. And if you have 4, you only have 1 position where you could be. And by the way, you can also correct for problems with your own time, because you don't have an atomic clock in your car, I assume. So that is how GPS fundamentally works. As an aside, does it mean that now that we have GPS, we can forget about all these other ways of navigating? Not necessarily. About a week or 2 ago, there was a news item that the plane with the president of the European Parliament could not use GPS because it was probably being jammed by the Russians. So they actually had to navigate with old flight maps. Luckily, they were still able to do that. So I want to briefly talk about another very accurate clock, clocks in the sky. I want to talk about neutron stars. But what are neutron stars? This is the one-slide summary of the life of a star. Stars start out basically as a gas and dust cloud, which collapses, and you may get a sun-like star that will happily fuse hydrogen into helium for about 10 billion years. Then it runs out of fuel. I won't go into details. It will turn into a red giant. It will shed off its outer layers, and you get what is known as a planetary nebula. They can be really beautiful. And then you get what is known as a white dwarf. It gets more spectacular if you have a more massive star, because now not only do you get a really super giant, you also get a big explosion at the end. The whole star is exploding, and what remains is either a black hole, which would be taught on its own, or a neutron star. Plus a very beautiful remnant of all the debris from the explosion which has been ejected. But what is a neutron star? A neutron star is basically a star with the same mass as the sun, or a bit more, with a size that fits into Cape Town. That is dense. If you have a tablespoon of neutron star matter, it would weigh about the same as Table Mountain, I think. So that's pretty massive. Now, these pulsars have a nice habit that charged particles are attracted by very high magnetic fields onto the poles, and radiation is emitted in 2 cones, really like a lighthouse. And these neutron stars are spinning, and they can spin very rapidly. And the cool thing is, in a very stable way, they are very accurate clocks. So we have very accurate clocks in the sky. And, oh, I might even have an animation of that. Or maybe not. And what can you do with neutron stars? I want to give you two examples. And the first one is we can actually learn about the fabric of space and time. We can find gravitational waves. What are gravitational waves? In a nutshell, you may have heard about Einstein and his theory of relativity. And his theory of general relativity basically tells us that if you have mass, space and time are warped. Really like a membrane in this image. And I won't go into the details, that's another story. But the important bit is if one mass makes a dent in the membrane, and now you have two masses, you will have two dents, right? And if you now start moving these two masses in the membrane, it should come as no surprise that you get a wave moving through the membrane. That works for space-time as well. You can have waves of space and time, and those are called gravitational waves. How would you measure them? Well, you can basically use two light beams and interference, and it is not easy. The length difference is length difference you have to figure out is way smaller than the size of a proton in a nucleus. And it has taken, I think, about 40 to 50 years from the conception to the eventual detection of gravitational waves. And the amazing thing is they got funding for that time, similar to Harrison getting funding for his clocks for such a long time. But that is one way, but I mention it because another way is, I just told you that we have accurate clocks in the sky, right? We have these neutron stars, these pulsars with very periodic time signals. So what I can do is I can observe several pulsars over a long time, and I can just time when their signals arrive. And if they're gravitational waves, these times should become a bit longer or shorter. And if I do very accurate measurements and throw in a lot of statistics, I can actually find very long-ranging gravitational waves with a frequency you would not be able to detect on Earth, with a detector like the one I just showed you, which was LIGO, by the way. And actually, it has been done. Radio telescopes can observe pulsars very accurately, and they have at least found good evidence of these gravitational waves. So another window into the universe. Another thing you can do with pulsars is shown here. How would you tell an alien where you live? I mean, it doesn't really help them to tell Earth, right? Because they won't know what that means. So one idea was, and that actually is a part of a pioneer plot, that, okay, you show the direction of several pulsars. They have a very well-defined frequency, so they should be identifiable for aliens. That is the idea. When you tell them in which direction are they, how far away are they, and from that, the aliens can figure out where to come and I don't know what to do with us. Maybe it's a good thing that we'll probably never find this plant, and I'm not convinced they would understand it. Remains to be seen. So, and that brings me back this whole thing of, well, spaceships, spacecrafts, to the problem of navigation. We have a navigation problem again. We've solved the problem on Earth. We still have a bit of a problem with spacecraft navigation. One key ingredient with spacecraft navigation is that you have to know how far, say, you are away from Earth. You can find that out by basically shooting a light signal and waiting for the return answer. And then just from the time delay, you can figure out the distance. But that means that you have this return journey. which can take quite a bit of time. And that's, of course, not good if you have made decisions very rapidly. But if your spacecraft has an accurate atomic clock on board, you don't need that anymore. Now you only need a one-way signal, because you can compare the time on Earth and your own time, because they both work accurately enough. And NASA is actually investigating that. So they really want to have very accurate atomic clocks on board of space probes for that very reason. So we are back again to the problem, knowing the time as precise as possible to find your way. Even these days, it may not find your way around the Earth, it may find your way around the solar system, and who knows, maybe further beyond at some point in the far distant future. Thank you so much for your attention.